When we talk about the cloud or about artificial intelligence, I feel like there is this almost overwhelming temptation for all of us to think of it as something entirely ethereal.
Oh, absolutely. The very language we use totally shapes that perception. Yeah.
Yeah, exactly. We talk about data floating in the ether, or we talk about neural networks as if they are just pure abstract thought.
And the word cloud itself just paints this picture of something weightless and silent, just hovering above us. It's brilliant marketing, honestly.
It really is, but it completely masks the physical reality. It makes the entire digital revolution sound like magic, totally divorced from the constraints of the physical world.
Right, which is a massive misconception. We are currently witnessing what is basically the ultimate collision between cutting-edge computer science and old-school, heavy industrial engineering.
That is the perfect way to frame it. Because the deeper you get into how this ecosystem actually operates, the more you realize that this supposedly weightless digital future is entirely dependent on some of the heaviest, most intensely physical infrastructure humanity has ever built.
Yeah, you can write the most elegant, sophisticated AI algorithm in the world, but eventually that code has to run on a physical piece of silicon.
Right, and when it does, it generates heat, a staggering amount of heat.
Exactly. If you strip away the sleek software interfaces on your phone, you are immediately confronted with brutal, heavy metal, massive electrical power draws, and the very real, very stubborn laws of thermodynamics.
And managing that heat is exactly what we're focusing on today. We're taking a deep dive into the literal physical circulatory system that is keeping the current AI boom from spontaneously combusting.
Which is a very real threat, by the way.
Oh, for sure. For this exploration, we have a fascinating stack of sources for you today. We're looking at a highly technical datasheet accompanied by a series of incredibly detailed engineering schematics and hardware images from a company called Supermicro.
And I have to say, these documents are far more revealing than your standard product catalog.
Yeah, how so?
Well, they provide a direct window into the absolute physical limits of modern computing architecture. And more importantly, they show how the industry is frantically engineering ways to push past those limits.
Okay, let's unpack this because we are moving from the abstract idea of a chatbot composing a sonnet to the intensely physical, heavy metal reality of data center plumbing. Our mission for this deep dive today, or for you listening, is to decode these blueprints.
Right. We're looking specifically at a piece of machinery called the Supermicro 4U InRack Coolant Distribution Unit, or CDU for short.
So our goal is to dissect these specifications in these vivid engineering images to understand exactly how hyperscale data centers are solving the massive thermal bottlenecks of high-density computing.
What's fascinating here is the sheer, inescapable necessity of this hardware evolution.
Yeah, this isn't just an optional upgrade.
Not at all. If we look at the broader context of the tech industry right now, rack densities for AI and high-performance computing, what we call HPC, are skyrocketing at a pace that is, frankly, terrifying for facility managers.
Terrifying is a strong word, but looking at the numbers, it makes sense. We are talking about packing so much raw processing power into a single standardized server rack that the power consumption of that one cabinet is hitting 250 kilowatts.
Right, 250 kilowatts in a space roughly the size of a kitchen refrigerator.
To put that in perspective for you, think about a typical ceramic space heater you might plug into your wall at home during the winter. That little device pulls about 1.5 kilowatts, right?
Yeah, usually around 1,500 watts.
And the metal grill on the front of that heater gets hot enough to severely burn your hand in seconds. We're talking about the thermal equivalent of shoving more than 160 of those space heaters into a single metal cabinet.
And running them at absolute maximum output 24 hours a day.
Exactly. And then trying to keep the highly sensitive microelectronics trapped inside that box from melting into a puddle of expensive slag.
The visual of 160 space heaters is remarkably accurate, and that immense thermal density is the exact reason why traditional air cooling is physically, fundamentally obsolete for these new workloads.
Because air just can't keep up anymore, right?
Exactly. For decades, data centers operated on a very simple premise, just blow freezing cold air into the front of the server and suck the hot air out the back.
But you simply cannot move enough cold air fast enough over these new chips to carry away 250 kilowatts of thermal energy.
Right. The physics of air as a medium just stop working. Air is actually a terrible conductor of heat compared to liquid.
So this data sheet we are analyzing today, this InRack CDU, it really represents a mandatory evolutionary leap in architecture.
It is absolutely not a luxury upgrade or a niche option. It is a fundamental requirement to keep the digital economy moving forward.
Well, before we dive into the microscopic details of how the fluid moves and all the digital protocols managing it, we need to pause and visualize what this machinery actually looks like.
Because it is quite a piece of equipment.
It really is.
Yeah.
Looking at these source images, the word that comes to mind is intimidating. It looks less like IT equipment and more like something you'd find in the engine room of a dreadnought.
The visual language of the device communicates its function perfectly. It is entirely utilitarian, built for extreme durability under constant brutal operation.
Let's start with the physical footprint listed in the specs. This unit is described as having a 4U form factor.
Right, which we should probably explain. For those who might not spend their days configuring server rooms, rack space is measured in standard units, simply called U's.
And 1U is exactly 1.75 inches thick, right?
Yep, 1.75 inches. So a 4U unit takes up exactly 7 inches of vertical space.
Out of a standard server rack that might stand about 6.5 feet tall, this CDU is just a relatively small slice, typically sitting right at the bottom.
But the density of this 7-inch slice, I mean, it's genuinely mind-boggling.
The weight specification is usually where the reality of liquid cooling hits network engineers the hardest. I'm looking at the two specific models listed on the datasheet, and the numbers are staggering.
They are heavy, very heavy.
The EIA standard model weighs 100 kilograms, and the OCP standard model weighs 114 kilograms.
We are talking about up to 250 pounds of mass compressed into 7 inches of vertical space.
And here is the truly wild part, that is the dry weight. That is the mass of the unit before you pump a single drop of liquid coolant into its internal reservoirs.
Right. You are looking at the combined density of heavy-gauge steel chassis components, massive industrial-grade dual pumps, incredibly dense copper piping manifolds, and the robust electrical circuitry required to drive it all.
It is the mechanical equivalent of trying to slide a solid cast-iron V8 engine block into a standard server rack. You look at this 4U slice and you realize it is essentially solid mass.
It definitely requires more than one person to lift.
Oh, absolutely. Let's talk about those two acronyms for a second, EIA and OCP, because the source material makes a very distinct point of highlighting that Supermicro builds a model for each.
Yeah, that's a really important distinction for the industry.
If I'm understanding the history of data center architecture correctly, EIA refers to the Electronic Industries Alliance Standard, which is your classic, ubiquitous 19-inch wide server rack that has been around since the days of early telecom equipment.
Your historical context is spot on there. The 19-inch EIA rack is the universal default of the IT world. If you walk into almost any enterprise server room on the planet, you will see rows and rows of 19-inch racks.
But the other model, the 114-kilogram behemoth, is built for the OCP standard. And OCP stands for the Open Compute Project.
Right, which is a much newer standard.
From what I recall, OCP was an initiative started over a decade ago by massive hyperscalers, primarily Facebook, now Meta, because the standard 19-inch telecom rack was wildly inefficient for their massive scale.
Exactly. The hyperscalers realized that standard enterprise gear was burdened with legacy design choices that wasted physical space and electrical efficiency.
So they designed a slightly wider 21-inch rack standard that completely rethought how power is distributed, moving away from individual power supplies in every server to a massive centralized power bus bar running down the back of the entire rack.
Yeah, by making the rack slightly wider at 21 inches and fundamentally changing the electrical delivery architecture, OCP racks can achieve higher density and better airflow.
The fact that Supermicro explicitly engineers two entirely different physical models of this CDU, one for legacy 19-inch EIA and one for modern 21-inch OCP hyperscale environments, that really proves this technology isn't just a bespoke solution for a single tech giant.
Absolutely not. They are providing the critical plumbing infrastructure for every tier of the data center market, from enterprise to hyperscale.
And when you look at the front-facing images of both models provided in the sources, you immediately see why this equipment requires such immense structural integrity. As I said earlier, it doesn't look anything like a computer.
No, there are no sleek plastic bezels or decorative airflow vents. It looks like serious, heavy industrial machinery.
The operational environment really dictates the design. You are placing highly pressurized liquid lines mere inches away from densely packed microelectronics, drawing hundreds of amps of current.
The margin for error is absolute zero. You cannot afford a leak.
I want to paint a vivid picture of this faceplate for you. Imagine a thick, brushed silver metal chassis. On the far left and far right sides, you have these massive, heavy-duty industrial handles protruding outward.
And these aren't the little flimsy plastic tabs you use to slide a standard server blade in and out.
Not at all. These are thick, machined metal grips bolted directly into the structural frame of the chassis. Because again, a technician might be maneuvering over 250 pounds of dense metal on sliding rails.
Right, the physical ergonomics have to match the mass of the unit.
Then, dominating the center and right side of the unit, you can clearly see the dual pump modules. Securing these modules are heavy mechanical pull-down latches.
The source images actually zoom in on these latches, and it is fascinating.
Yeah, they have literal step-by-step instructions printed in bold, utilitarian lettering right on the bare metal. One step says 2, push down on the latch with a little P indicator, and another says 1, keep pressing the handle.
It has this distinctly mechanical, almost aviation-grade or maritime feel to it.
Exactly. You don't just click a plastic tab into place, you engage a heavy mechanical lever. You lock it down to compress the O-rings and seal the fluid paths.
That tactile, highly mechanical design is not just an aesthetic choice, It is a critical safety feature for the human operators.
Because they need to know it's secure.
Right. When a technician is dealing with a closed-loop fluid system inside a rack containing millions of dollars of AI hardware, they need absolute, undeniable physical certainty that a component is seated, locked, and sealed correctly.
A satisfying mechanical clunk from a heavy latch provides a level of assurance that a digital indicator simply cannot replace.
Exactly. But then, juxtaposed immediately next to all that heavy, brutalist industrial metal, on the left side of the front panel, there is a very sleek, modern, integrated touchscreen display.
A fully digital diagnostic interface embedded directly into the physical plumbing. It's quite a contrast.
It really is. The source image provides a brilliant close-up of this screen, and the amount of telemetry it displays is incredible.
It's a full-color graphical interface.
Yeah.
And you can see the digital readouts capturing the physics of the machine in real time.
Yeah, it displays the basic identity, the CDU name, along with the overarching system status and the active power source.
But then it dives into granular mechanical metrics. It shows the precise rotations per minute, the RPMs, of the left and right pumps individually.
I think the image captures one pump spinning at exactly 6,390 RPM.
That's incredibly fast. It also tracks the real-time fluid flow rate in liters per minute, the precise supply and return temperatures of the liquid, the active status of the leak detection sensors, and the physical liquid level inside the internal reservoir.
It is a comprehensive, mission-controlled dashboard embedded directly into this dense metal box, which is amazing.
This specific integration of digital telemetry and heavy mechanical pumping brings us to a foundational concept highlighted in the source document.
Right, where Supermicro describes this architecture as having compact integration with plug-and-play deployment.
Now, plug-and-play is a colloquial term we usually associate with consumer electronics, like plugging a new USB webcam into your laptop and having it work instantly.
It implies a frictionless simplicity.
But what we are observing here is an engineering triumph on an entirely different scale.
Yeah.
They have taken an industrial system that historically required an entire dedicated mechanical room in a building, a room filled with massive floor-mounted pumps, huge holding reservoirs, and complex custom-welded plumbing networks, and they have condensed all of that into a standardized slide-in 4U chassis.
Right, running into raised floorboards and all that. To really drive home what it means to condense this technology, there's another image buried in the source material that shows a stripped-down internal view of a much larger, older-style facility cooling unit.
Oh yeah, the contrast is jarring. The older unit looks like the mechanical guts of a nuclear submarine.
It is an absolute forest of thick, vertical copper pipes crisscrossing each other.
There are massive heavy metal valves with bright red manual turn handles. There is literally a giant red mushroom button on the front panel labeled EMO Emergency Machine Off.
It screams serious, bespoke, dangerous industrial plumbing.
The older architectures were massive custom engineering projects for every single building, weren't they?
They absolutely were. The brilliance of this specific 4U InRack CDU is that it takes that exact same massive industrial plumbing capability and shrinks it down, placing the primary pumping mechanism directly inside the specific rack it is meant to serve.
Which, purely from an intuitive standpoint, seems a bit wild to me.
Yeah.
You're taking high-pressure water pumps and placing them inches away from the absolute heart of the most expensive electrical equipment in the building.
It does sound deeply counterintuitive to mix water and high voltage so intimately. I totally agree. Until you examine the physics of fluid dynamics that the datasheet is referencing to justify this design.
Right, the datasheet gets into the weeds on this.
Yes. By installing the CDU directly at the bottom of the rack, Supermicro explicitly states in the specs that this architecture shortens coolant loops and minimizes pressure drop.
Let's break down the physics of pressure drop because it feels like the key to this whole design.
Mhm.
If I can try an analogy here, if I'm watering my garden with a standard 50-foot garden hose, the water comes out of the nozzle with a certain amount of force, right?
Yeah.
But if I decide to attach another 200 feet of hose to reach the far side of my yard, by the time the water travels all that distance, it just sort of trickles out weakly at the end.
Because of the friction.
Exactly. That loss of kinetic force over a physical distance due to the friction of the water dragging against the inside of the hose, that's pressure drop, correct?
That analogy captures the mechanics perfectly. Every single inch of pipe, every joint, every bend, and the inherent viscosity of the fluid itself creates friction and resistance.
Okay, so map that analogy onto a massive hyperscale data center for us.
Right. If your main water pump is sitting in a centralized mechanical room that is 200 or 300 feet away from the server rack it needs to cool, that pump has to work incredibly hard.
Because it's pushing water through hundreds of feet of pipe.
Exactly. It has to push the water all the way through the building's underfloor piping, force it up into the rack, and then here's the most difficult part, shove it through the microscopic, densely packed copper channels inside the cold plates that are physically mounted on top of the processors.
And those microchannels must create immense back pressure.
Massive back pressure. And finally, the pump has to pull all that water all the way back across the building. That vast distance creates massive resistance.
And to overcome that massive resistance, to force the water through those tiny processor channels from a football field away, you would need absolutely massive, incredibly energy-hungry central pumps.
You would need industrial pumps drawing immense amounts of power. And crucially, you'd be putting the entire multi-hundred-foot piping system under immense, dangerous static pressure just to force the water that far.
Which sounds like a recipe for a disaster.
It is. Higher pressure across a sprawling network exponentially increases the risk of catastrophic leaks at any joint or valve.
So by placing this 4U CDU directly at the bottom of the rack, the physical distance the coolant has to travel is reduced to mere feet.
Precisely. The pump pushes the liquid up a short vertical manifold to the servers directly above it. The liquid absorbs the heat from the processors, and it drops right back down into the CDU.
The loop is incredibly short and localized.
Exactly. Because the loop is so short, the pressure drop is almost entirely negated. The water moves incredibly quickly and efficiently, maximizing the thermal transfer away from the silicon.
And the overall reliability of the data center vastly improves because the plumbing system isn't straining against miles of pipe resistance, and you aren't pressurizing the entire building.
Which naturally brings us to a massive architectural concept highlighted in these sources, the design philosophy of the cooling loop itself.
Right, because if we play out the logic of putting a pump in every rack, a question immediately pops up for you listening. Let's say a company is building a new AI data center designed to house 1,000 server racks.
A very standard deployment size these days.
Why on earth would the engineers choose to install a separate 250-pound heavily engineered pumping unit into every single one of those 1,000 racks? Wouldn't it be infinitely cheaper, simpler to maintain, and more spatially efficient to just build one massive centralized pumping station for the whole building?
Basically applying a municipal water tower model to server cooling.
Yeah, exactly.
Well, you have just outlined the exact architectural debate that has defined data center mechanical engineering for the last decade. Centralized versus distributed cooling.
And the source document provides Supermicro's definitive, uncompromising answer to that debate under a section headed Dedicated Cooling Loop for Reliability.
Yes. Let's dissect the wording there. What does a dedicated loop actually mean in practical mechanical terms?
Well, in this context, dedicated means complete, uncompromising physical isolation.
It means that every single InRack CDU operates entirely independently of the others. It serves the compute nodes in its specific rack and absolutely nothing else.
There is zero shared fluid, zero shared pressure lines, and zero shared mechanical dependency between Rack A and Rack B.
So it is an entirely closed, localized ecosystem, complete isolation.
To understand why this is so critical, consider the financial and operational reality of modern artificial intelligence training.
Right, an AI cluster isn't just a collection of random computers serving up websites.
No, thousands of GPUs across hundreds of racks are all networked together, functioning as a single, massive supercomputer, working in parallel on a single, incredibly complex mathematical problem, like training the next generation of a large language model.
So if one single rack goes offline due to a thermal failure, it doesn't just impact that rack, it can stall the entire training run.
Potentially forcing the engineers to roll back to a previous save state, which they call checkpointing. When compute time on a cluster like that costs hundreds of thousands of dollars per day, a cooling failure is a staggering financial event.
The stakes aren't just high, they're astronomical. The infrastructure has to be infallible.
It does. So let's return to your analogy of the single giant pump, the municipal water tower model serving the whole building.
Right. If that centralized pump experiences a mechanical failure, or if there's a major pressure drop in the main facility trunk line, or a catastrophic leak in the primary header, it takes down the cooling for the entire building simultaneously.
The entire multi-million-dollar AI cluster goes into thermal runaway and shuts down in seconds.
It creates a massive single point of failure for the entire facility. It is an unacceptable level of systemic risk.
By dictating that one independent CDU is dedicated to one single rack, Supermicro effectively eliminates that systemic building-wide risk.
The source document explicitly notes that the strict isolation, quote, prevents any impact on other IP equipment, while eliminating risks of leakage or pressure drop from cascading like dominoes through a facility.
In military or cybersecurity terms, it essentially limits the blast radius of any potential hardware failure.
Limiting the blast radius is the perfect conceptual framework. If, in the absolute worst-case scenario, a pump inside a CDU fails catastrophically and the backup fails as well, you lose the processing power of that one specific rack.
But the other 999 racks in the data center, completely unaware of the failure because they each have their own dedicated CDU, continue operating perfectly.
You have successfully contained the thermal blast radius to a single cabinet. The source defines this architecture as ensuring stable cooling for mission-critical workloads.
It is entirely about the intelligent compartmentalization of physical risk.
Absolutely. And within that tightly compartmentalized, highly isolated rack, the sheer volume of thermal energy this unit is rated to handle is staggering.
The specifications boldly claim that each CDU delivers up to 250 kilowatts of cooling capacity.
We talked about the 160 space heaters analogy earlier to visualize the heat, but let's translate that 250 kilowatt number back to the computing hardware itself.
What does that specific capacity metric actually empower a data center architect to do?
It empowers them to radically alter the physical geometry of their computing clusters. It allows them to pack exponentially more powerful GPUs and CPUs into a single vertical footprint than was ever possible with air cooling.
Because in the traditional air-cooled past, if you were deploying hardware that generated 250 kilowatt total heat load, you simply could not put it all in one cabinet.
Not even close. You would have had to spread those servers out horizontally, distributing them across perhaps 5, 6, or even 8 different racks, just so the massive room-level air conditioners could force enough cold air through the dispersed equipment to keep it from melting.
So you were essentially paying for vast amounts of empty, unproductive floor space purely to manage the thermodynamics. Data center design wasn't just an electrical engineering problem. It was a massive real estate and geometry problem.
You were paying premium commercial real estate prices just to give the hot air enough physical room to dissipate. The physical footprint was dictated entirely by thermal limitations.
With this InRack CDU managing a massive 250 kilowatt heat load locally within the cabinet, architects can consolidate all that scattered compute power into one single ultra-dense rack.
They maximize the compute density per square foot. Furthermore, because liquid transfers heat so much more efficiently than air, the silicon chips themselves, the GPUs, can run at their absolute maximum clock speeds indefinitely without triggering thermal throttling.
And thermal throttling is a protective mechanism where a processor deliberately slows its own performance down to reduce heat generation and avoid physical damage. Right?
Exactly. The CDU carries the heat away so rapidly and effectively that the silicon never reaches that danger zone. It can simply scream along at peak performance prominently.
Okay, that compute density is incredible, but it immediately brings up a terrifying counterthought.
Uh-oh. What is it?
We have just established that the entire rack, which is now densely packed with millions of dollars of the latest, most powerful GPUs, is entirely 100% reliant on this single 4U metal box sitting at the bottom of the cabinet.
Right, the isolated loop.
We contain the blast radius to one rack, yes, but for that specific ultra-expensive rack, this CDU has become a terrifying single point of failure.
Ah.
If the water stops circulating for even a few seconds, 250 kilowatts of contained heat will literally melt those processors into slag before a human technician could even run down the aisle.
Oh, well,
What exactly happens if this specific machine breaks?
you are voicing the existential dread that keeps every data center manager awake at night. And Supermicro knows this, which is exactly why the source document dedicates a massive portion of its technical overview to what I would describe as a fortress of uptime.
The layers of engineering redundancy built into this local system are exhaustive. The source is remarkably blunt about the reality of the situation.
It explicitly states, when it comes to mission-critical deployments, even brief periods of downtime can have significant impact on data center operations and productivity.
They aren't sugarcoating what is at stake. To counter this, they have engineered what looks like a triple threat of hardware failsafes.
The architecture is built on the philosophy of assuming components will eventually fail. They engineered deep redundancy across all the critical operational vectors: the primary fluid pumps, the microcontrol units, or MCUs, that act as the digital brains, and the power supply units, or PSUs, that provide the electricity.
Here's where the granular details of the specifications get genuinely fascinating to me. When you look closely at the exact specifications table at the very bottom of the datasheet, comparing the EIA model to the OCP model, there is a very distinct major difference in how they approach pump redundancy.
The engineering divergence between the two standards?
Exactly. Let's look at the numbers. We have the EIA standard model part number ACS SCDU 250L401. The spec sheet explicitly lists this model as having 2N redundant pumps and states its maximum power consumption is 1.2 kilowatts.
Okay, so that's the 19-inch model.
Right. Then, in the column right next to it, we have the OCP standard model part number LCS SCDU 250LP4002. This model is listed as utilizing N+1 redundant pumps, but its maximum power consumption skyrockets to 3 kilowatts.
A massive jump in power.
Before we even get to the power draw, what on earth is the practical mechanical difference between a 2N system and an N+1 system? Because if I am spending a fortune on a fail-safe mechanism, I want to know the exact mechanics of how it fails safely.
The difference between 2N and N+1 is a foundational concept in critical infrastructure design, highlighting how engineers balance ultimate ironclad security against physical constraints and efficiency.
Let's define the terminology first.
Right. The letter N always represents the baseline essential capacity required to perform the task. In this scenario, if it takes a specific amount of fluid pressure and flow rate to extract 250 kilowatts of heat from the rack, that baseline required flow rate is N.
Okay, so N is the absolute minimum viable performance to keep the silicon from melting down.
Correct. So, examining the EIA model, it boasts 2N redundancy. This indicates a 100% mirrored backup architecture. It means you have exactly twice the necessary physical equipment.
If the thermodynamic math requires one massive pump to achieve N, a 2N system features two completely independent, identically massive pumps.
Yes. During normal operation, one primary pump handles the entire 100% load of the rack. The second pump sits there, completely idle or perhaps running at a barely perceptible low RPM purely to keep its internal bearings lubricated, doing nothing but waiting for the primary pump to suffer a mechanical failure.
If I can use an analogy, it's like a twin-engine commercial airplane that is fully capable of taking off, flying, and landing on just one single engine, but the airline installs two full-sized engines just in case one ingests a bird.
A very apt comparison. In a 2N cooling system, if pump A physically seizes up or loses power, pump B instantaneously spins up and assumes the entire 100% cooling load.
There is virtually zero drop in fluid pressure, and the servers never even register a temperature spike. It is the ultimate brute force approach to reliability.
Now, contrast that architecture with the OCP model, which utilizes N+1 redundancy.
Which, confusingly to me, has a drastically higher maximum power draw of 3 kilowatts.
The power draw is a clue to the mechanical complexity. In an N+1 architecture, N still represents the baseline capacity required, and the +1 represents a single additional backup component.
However, the physical configuration is usually fundamentally different.
Exactly. Instead of having two massive, 100% capable pumps where one does all the work, an N+1 system often distributes the workload. For example, it might utilize 3 slightly smaller pumps.
So it requires the combined simultaneous effort of 2 of those pumps to meet the baseline N requirement, and the third pump acts as the +1 backup.
I am starting to see how the workload distribution shifts. In a typical N+1 deployment, during normal, healthy operations, all 3 smaller pumps might run simultaneously, continuously sharing the total cooling load.
They operate at a lower, more efficient capacity.
If one of those three pumps suffers a failure, the system recognizes the pressure drop, and the remaining two healthy pumps immediately spool up to higher RPMs to compensate and maintain the critical baseline N requirement.
So why does the N+1 OCP model have such a massive discrepancy in power consumption? Why does it draw a maximum of 3 kilowatts, while the brute force 2N EIA model only draws 1.2 kilowatts? That seems inverted.
Well, while the provided datasheet doesn't offer a deep dive internal electrical schematic, we can deduce the reasoning based on the engineering principles of the Open Compute project. OCP architectures often utilize entirely different power delivery mechanisms, sometimes relying on higher voltage inputs or different phase power delivered directly from the rack's bus bar.
So it might just be a symptom of the OCP environment itself.
It's highly probable that the specific pumps chosen for the N+1 OCP model are individually more powerful to support higher flow rates, or more likely the internal fluid manifold, the complex piping system that dynamically balances and routes the pressure between multiple active pumps, requires sophisticated, energy-intensive electronic valves to manage the flow perfectly when a pump fails.
The critical takeaway for anyone analyzing this is that Supermicro isn't forcing a one-size-fits-all solution.
Right, they are offering two distinctly different philosophical and mechanical approaches to redundancy, allowing facility engineers to match the equipment to the specific electrical and spatial constraints of their chosen rack architecture.
The ultimate goal of both philosophies is achieving what the source document dramatically calls uninterrupted power continuity and cooling reliability.
The inclusion of redundant power supply units, the PSUs, is just as critical.
It ensures that even if one of the primary electrical circuits feeding the data center rack physically trips a breaker, the CDU instantly falls back to a secondary power circuit without dropping offline.
The redundant power keeps the redundant pumps spinning because, as we discussed, the timeline for disaster is incredibly compressed.
If fluid circulation stops in a rack generating 250 kilowatts of heat, the facility technicians do not have minutes to diagnose the issue and respond.
No, they have a matter of seconds before catastrophic thermal failure destroys millions of dollars of hardware. These deep layers of redundancy guarantee that the thermodynamic performance remains stable under virtually any physical or electrical failure condition.
Okay, so we have firmly established the heavy metal realities of the hardware. We've explored how the dual pumps move the fluid safely, how the blast radius of a failure is contained to a single rack, and how deep redundancy prevents catastrophe.
Now, I want to pivot and talk about the fluid itself.
Yes, because this specific topic brings us to what I found to be the most counterintuitive, genuinely surprising, and fascinating revelation in this entire stack of engineering sources.
You're referring to the thermodynamics of the coolant loop.
Yes, the thermodynamics. There is a specific bullet point under the heading Ultimate Cooling Performance that genuinely stopped me in my tracks when I first read it.
I know exactly which one you mean.
It states, power and cost optimized, supports warm water up to 45 degrees C. Now, for those of us who use Fahrenheit, 45 degrees Celsius translates to roughly 113 degrees Fahrenheit.
Which is very warm.
I am certainly not a physicist, but I possess a basic human understanding of how it feels to be hot. If I am overheating and sweating on a blistering summer day, my instinct is absolutely not to jump into a 113-degree shower to cool off.
That sounds like a form of torture.
Exactly.
Yeah.
How on earth, physically and logically, does warm water effectively cool down a hyper-advanced supercomputer that is generating 250 kilowatts of heat and is on the verge of melting?
It is a brilliant question, and it beautifully illustrates the massive gulf between human sensory intuition and the rigid laws of thermodynamics.
Okay, lay it on me.
To grasp how this works, we have to fundamentally discard the concepts of hot and cold as absolute fixed states and start analyzing them strictly as relative differences.
Okay, I am going to try to unpack that. Let's look at relative differences. If the first law of thermodynamics is roughly that heat always flows from a higher temperature environment to a lower temperature environment, then the speed and efficiency of that heat transfer must depend on the difference between those two temperatures, right? The delta.
You're hitting on the core physics perfectly. Heat transfer is driven by the delta, the temperature gradient. Now, consider the operational reality of a modern high-performance GPU under a massive computational load.
The actual silicon die inside that processor isn't running at a pleasant human body temperature?
No, under full load, that silicon can easily and safely operate at 90, 100, or even 110 degrees Celsius.
100 degrees Celsius is literally the boiling point of water.
It is. So place yourself in the perspective of a piece of silicon that is currently baking at 100 degrees Celsius. To that silicon, water flowing past it at 45 degrees Celsius does not feel warm. It represents an incredibly drastically colder environment.
Because the physical difference between the 100-degree silicon chip and the 45-degree water is still a massive 55 degrees.
The math backs that up entirely. That 55-degree delta creates a massive, steep temperature gradient. When that 45-degree fluid enters the microscopic copper channels of the cold plate sitting directly on top of the processor, Fourier's law of thermal conduction takes over.
The massive amount of thermal energy trapped in the silicon violently and rapidly rushes into the fluid to try equalize the temperature.
The water absorbs that immense heat, perhaps warming up to 55 or 60 degrees Celsius in the process, and the pumps rapidly evacuate it from the rack, taking the heat energy away with it.
Liquid has an incredibly high specific heat capacity, meaning it can absorb a vast amount of energy before its own temperature rises significantly.
Right. Mechanically, the physics make perfect sense when you frame it around the delta.
But this raises a major operational question. Why engineer the system to use 45-degree warm water on purpose? If cold is relative, why not use perfectly chilled refrigerator cold water at, say, 10 degrees Celsius? Wouldn't a 90-degree delta cool the chips even faster and provide a wider margin of safety?
While it would technically extract heat faster, employing artificially chilled water introduces a catastrophic penalty in terms of facility efficiency. And this specific engineering choice is where the source material transitions from clever plumbing to a massive financial and environmental paradigm shift for the industry.
The datasheet explicitly claims that supporting warm water up to 45 degrees C is eliminating the need for mechanical chillers, reducing PUE and overall operational costs.
We absolutely need to define PUE for the listener because it seems to be the central metric governing data center economics.
PUE stands for Power Usage Effectiveness. It is the golden overarching metric of the entire data center industry.
It is a simple ratio that describes exactly how efficiently a facility utilizes its electrical power. A perfect, theoretically impossible PUE is 1.0.
A PUE of 1.0 would mean that every single watt of electricity pulled from the local grid goes directly into powering the IT equipment, the servers doing the actual computational math.
Which is physically impossible because a building needs lights, security systems, and most critically, cooling infrastructure.
The cooling infrastructure is the massive variable. Historically, a decade ago, traditional air-cooled data centers routinely operated with dreadful PUEs of 2.0 or even higher.
A PUE of 2.0 means that for every 1 megawatt of power the facility spent actually running the servers, they were forced to purchase and burn another entire megawatt of power just running massive building-sized air conditioners to keep those servers from overheating.
So they were essentially doubling their electric bill and their carbon footprint just fighting the heat their own product generated. It's an incredibly vicious, expensive cycle.
It was an unsustainable model. To achieve cold air, or to artificially chill water down to 10 degrees Celsius, a facility has to utilize mechanical chillers.
Mechanical chillers are fundamentally gigantic industrial refrigerators.
They rely on complex thermodynamic cycles involving chemical refrigerants, expansion valves, and crucially, massive mechanical compressors to artificially crush the heat out of the system.
Running massive compressors requires enormous continuous amounts of electricity.
So by intentionally designing this InRack CDU, the fluid manifolds and the server cold plates to efficiently operate with fluid that is already naturally warm at 45 degrees Celsius or 113 degrees Fahrenheit, what profound architectural change are they enabling for the facility?
They're entirely deleting the industrial refrigerator from the facility blueprint. They are bypassing the compressor completely.
Think about the global climate. If your hardware is designed to safely cool itself using 45-degree water, you no longer need to burn massive amounts of electricity artificially chilling that water down.
Because in virtually any geography on the planet, even in the middle of summer, in a scorching desert environment, the ambient outside air temperature is cooler than 45 degrees C.
That is a staggering realization. 113 degrees Fahrenheit is considered a brutal, potentially lethal heat wave for humans in most parts of the world, but to this machine, it is a perfectly acceptable cooling medium.
The operational implications are massive. Instead of running a power-hungry chiller, all the data center has to do is pump the 60-degree hot return water from the server racks outside the building to a simple passive radiator system.
They let the ambient outside air blow over the radiator coils to naturally extract the heat and drop the water temperature back down to 45 degrees C, and then they pump it right back inside to the CDU.
The facility completely avoids spending electricity refrigerating the water. They only have to spend a tiny fraction of that electricity simply moving the water with pumps and running a few fans.
You are solving an intense thermodynamic problem not by fighting against physics with brute force electrical refrigeration, but by intelligently harmonizing with natural ambient temperature gradients.
The financial and environmental results are transformative. By eliminating the chillers, facility PUEs plummet from 2.0 down toward 1.1 or 1.05.
It saves hyperscalers literally millions of dollars in operational electricity costs annually, frees up grid power to be used for more compute rather than cooling, and radically reduces the environmental carbon footprint of these massive AI factories.
It is a profound example of elegant, consequential engineering. It genuinely is incredible. It takes this heavy, intimidating, brutalist piece of machinery, this 250-pound block of pumps and muddle, and reveals it to be the key to a highly elegant, environmentally optimized ecosystem.
However, to flawlessly orchestrate all of this physical complexity, managing the redundant pumps, monitoring the fluid dynamics, tracking the temperature gradients, and ensuring zero leaks, a system this powerful and mission-critical cannot just be a dumb, purely mechanical pipe.
It needs a digital brain, and crucially, it needs the ability to communicate with the rest of the data center software infrastructure.
We're transitioning now from the realm of physical plumbing into the realm of the digital command center. The InRack CDU must serve as a seamless bidirectional bridge between raw physical hardware and high-level network software.
And the datasheet is incredibly explicit about this digital capability. Under the Integration and Management section, the source lists an absolute alphabet soup of networking protocols.
It proudly states that the unit supports Redfish, SNMP, V2C, and V3, a RESTful API, a standard web-based UI, and integration with something called Supermicro SuperCloud Composer, or SCC.
Now, I understand on a basic level that these are various protocols allowing computers to communicate over a network. But the obvious question is, why does a piece of industrial plumbing, a water pump, require a RESTful API and complex network protocols?
Because in the context of a modern hyperscale data center, this device is no longer just a water pump. It has been elevated into an advanced, highly critical IoT Internet of Things device.
Let's systematically break down what those specific protocols actually enable for the human beings and the automated software systems running the facility. Let's start with the foundational monitoring protocols, SNMP and Redfish. How do those function in this environment?
Well, SNMP, or Simple Network Management Protocol, is a legacy, deeply established standard used for decades to monitor network-attached devices like routers and switches.
And Redfish is a much newer, modern, incredibly robust, RESTful standard designed specifically by the industry to manage massive fleets of hardware at scale securely.
By natively supporting both, the InRack CDU is effectively stating I can plug into any existing facility management software on Earth, old or new.
Consider the sheer scale of a hyperscale facility. If you are managing a building containing 10,000 individual racks, you absolutely cannot rely on human technicians walking down miles of aisles, manually inspecting the physical touchscreen on every single 4U unit to ensure the fluid levels are nominal.
Attempting to manage an AI cluster that way would be like trying to monitor the health of a massive city's water grid by occasionally looking down individual storm drains. It's impossible.
The scale demands automation. You need every single piece of telemetry, the specific RPMs of the redundant pumps, the precise inlet and outlet temperatures, the current power draw, and critically, the instant status of the capacitive leak detection cables routed under the rack, streaming continuously and flawlessly to a centralized remote dashboard.
That is exactly what Redfish and SNMP facilitate. The central facility software can monitor the health, pressure, and temperature of every single drop of coolant in the building from a control room located hundreds of miles away.
But monitoring is only half the equation. It is purely passive. Which brings us to the inclusion of the RESTful API.
This is where things get really cool.
When I hear the term API, Application Programming Interface, I generally think about software applications exchanging data. It's how a weather app on a smartphone pulls live data from the National Weather Service servers, or how a travel website pulls flight prices from an airline. How does an API interface with a physical fluid pump?
This is where the engineering crosses into truly advanced workload orchestration. To understand the physical to digital bridge, we have to look inside the chassis. The physical components, the spinning magnetic impellers inside the pumps, the thermistors measuring temperature, the pressure transducers in the pipes are all analog devices.
They generate physical signals.
The CDU contains a microcontrol unit, an MCU, which acts as the local brain. The MCU constantly reads these analog signals, digitizes them into data packets, and exposes that data through the API.
Crucially, the API is bidirectional. It doesn't just send data out. It accepts commands in. It allows the actual software running the AI workloads to talk directly to the physical cooling plumbing.
So if I'm conceptualizing this correctly, with a RESTful API, we are looking at a scenario where the artificial intelligence software can actually proactively warn the plumbing about what it's about to do.
For example, the software orchestrator knows that in exactly 30 seconds, it is going to launch a massive new training epoch, and thousands of GPUs are going to instantly spin up to 100% utilization. It knows a thermal tidal wave is coming.
That is the exact scenario. If the cooling system relies purely on reactive mechanical sensors, it will not increase the pump speed until the thermistors physically register that the water is already getting dangerously hot.
By the time the pumps spool up, the silicon might have already initiated thermal throttling, ruining the efficiency of the training run.
But by utilizing the RESTful API, the workload orchestration software can send a digital command directly to the CDU's MCU before the computational workload even begins.
You can send a packet saying, a massive thermal load is imminent. Spool the redundant pumps up to maximum RPM immediately to pre-cool the loop.
It completely flips the paradigm. It transforms the physical infrastructure from being sluggishly reactive to being intelligently proactive.
The software workload and the physical hardware infrastructure cease to be separate domains. They merge into a single, unified, intelligent organism.
That holistic integration is precisely what Supermicro's SuperCloud Composer platform is designed to manage. It provides a single pane of glass that seamlessly orchestrates the IT hardware, the servers, switches, and GPUs, in perfect lockstep with the facility hardware, the CDUs, pumps, and fans.
This elegant synthesis of software and physical plumbing perfectly transitions us to the final, sweeping piece of the puzzle provided in the source material.
We have spent this entire deep dive hyper-focused on dissecting this one incredibly dense 4U box sitting isolated at the bottom of a server rack.
But the datasheet brilliantly includes a visual tour of the broader ecosystem. It zooms out significantly to show us exactly where this 45-degree warm water actually goes once the local CDU pumps it out of the rack.
They are illustrating the complete end-to-end architecture, what they term the Data Center Building Block Solutions, or DCBBS.
The images provided at the very bottom of the document paint a vivid picture of a massive, modular industrial infrastructure. I want to describe these components in detail for you because they truly capture the staggering physical scale of what we are discussing.
It really contextualizes the 4U unit.
First, they highlight these massive structures called dry coolers. Looking at the engineering photos, they literally resemble massive steel shipping containers, painted pristine white, sitting outside the facility.
But instead of a solid metal roof, the entire top surface of the container is composed of 2 long rows of giant, heavy-duty industrial fans pointing straight up at the sky.
Those dry coolers are the passive radiators we discussed earlier. That is the destination for the 60-degree hot water leaving the data floor.
The internal pumps circulate that hot fluid through massive banks of thin copper coils inside the container, and those giant upward-facing fans draw the ambient outside air across the coils, extracting the heat and exhausting it into the atmosphere, returning the fluid to the optimal 45 degrees C before sending it back inside.
Moving beyond the dry coolers, the next image shows a towering water cooling tower. This structure is genuinely imposing. It's a huge, vertically ribbed white tower that looks the size of a small commercial building.
It is so large it has a literal caged safety ladder attached to the side, leading up to a maintenance platform at the very top.
And at the base, mounted securely on solid concrete foundation blocks, are these massive, bright blue industrial water pumps connected to incredibly thick, white PVC piping running vertically up the sides.
Those towering structures utilize evaporative cooling. While dry coolers rely purely on air blowing over a closed loop of pipe, a cooling tower actually exposes the water to the air and utilizes the physics of evaporation, the latent heat of vaporization, to achieve massive amounts of heat rejection.
They are deployed when a facility requires more aggressive cooling capacity than a dry cooler can passively provide, perhaps in slightly warmer climates or for extreme density clusters.
And finally, rounding out the ecosystem, they show an image of a rear door heat exchanger.
This one is visually wild. At first glance, it looks like a standard enclosed server rack. But the rear door of the rack is swung wide open, revealing that the entire physical door is essentially one giant rack-sized radiator coil.
And embedded directly into this heavy metal door is a tightly packed grid of 10 large fans, which are glowing with an incredibly intense, almost sci-fi green LED light.
The rear door heat exchanger represents another highly modular approach to liquid cooling. Instead of running liquid directly to cold plates on the chips inside the server, the liquid circulates through the radiator built into the rear door.
As the server's internal fans blow the 250 kilowatts of hot air out the back of the chassis, it immediately passes through the chilled radiator door.
The heat is captured and neutralized before it even has a chance to enter the ambient air of the data center room. It is a highly effective localized heat trap.
What genuinely strikes me when analyzing all these images together, the shipping container-sized dry coolers, the towering evaporative water towers, the glowing green rear doors, and our dense, heavy 4U InRack CDU is how uniformly standardized it all looks.
It looks like a catalog of Lego bricks for building a supercomputer.
You have identified the ultimate, most consequential conclusion we must draw from this entire stack of source material. The 4U InRack CDU is not an isolated experimental prototype.
It is just one highly refined, modular piece, the vital internal organ, the beating heart of a massive, highly standardized, end-to-end global deployment system.
The standardization is explicit. The datasheet makes a point to mention that the unit is fully compatible with both EIA and 21 OCP standards.
It even goes so far as to specifically list an accessory adapter bracket. Part number LCS Patex is SSC0000. They have literally engineered and cataloged the exact metal bracket required to ensure this complex fluid pump can seamlessly slide into virtually any data center architecture on Earth.
What this deep level of standardization proves to the industry is that direct-to-chip liquid cooling has definitively crossed a major historical threshold.
For the past 20 years, liquid cooling was viewed as a custom, bespoke science experiment. If a university wanted a liquid-cooled supercomputer, it required hand-built manifolds, custom plumbing, and unique, non-repeatable engineering.
Supermicro's approach proves that this technology has now transitioned into standardized, massively scalable, off-the-shelf enterprise infrastructure.
Facility architects can now order these complex thermodynamic components like simple building blocks.
If a hyperscaler decides they need 10 megawatts of new AI compute capacity next quarter, they simply open a catalog and order X number of OCP racks, X number of InRack CDUs with N+1 redundancy, and X number of dry coolers.
The entire process of deploying liquid cooling has been industrialized. It is the complete industrialization of the digital circulatory system.
So to synthesize this entire incredibly dense journey for you listening, we started by looking at what appeared to be just a heavy 250-pound metal box equipped with a digital touchscreen and some heavy-duty aviation latches.
But by deeply decoding the physics and engineering embedded in these sources, we uncovered a localized, highly redundant, and incredibly energy-efficient circulatory system.
We explored a system that leverages the relative physics of warm 45-degree water to eliminate power-hungry mechanical chillers, intelligently isolates physical risks to contain the blast radius of hardware failures, and proactively communicates via advanced APIs with network software to ensure the current artificial intelligence boom doesn't literally melt the data center to the ground.
We are documenting a profound, permanent shift in how humanity builds the physical foundations of the internet. The era of simply blowing cold air over hot metal is over.
It's completely over.
So as we wrap up this massive deep dive, I have to ask the ultimate question. What does this level of engineering mean for the future? We're examining a mechanical system designed to handle a staggering 250 kilowatts of heat per rack today. Where does this trajectory ultimately take us?
Analyzing this source material inspires a very provocative, somewhat humbling final thought. We are rapidly approaching a unique point in history where the primary limiting factor in human technological advancement is no longer just our ability to design smaller, smarter silicon transistors or our ability to write more elegant, complex neural network algorithms.
The ultimate bottleneck to the future of AI is quite literally our ability to master advanced fluid dynamics, thermodynamics, and heavy industrial plumbing.
We are currently tasked with building the massive mechanical circulatory systems required to sustain our expanding digital brains.
The heavy metal plumbing is the fundamental enabler of the weightless digital intelligence.
The physics demand it. As the AI models become exponentially more complex, the silicon processing them will inevitably get hotter. The entire future of artificial intelligence, the pace of its evolution, depends entirely on how efficiently and reliably human engineers can move liquid water through dense metal pipes.
So as you watch the next massive leap in AI capabilities unfold over the coming years, as the models get smarter, faster, and more integrated into our lives, don't just think about the ethereal code floating invisibly in the cloud.
Think about the 250 kilowatts of blistering, physical heat being silently, continuously carried away by perfectly engineered, deeply redundant loops of 45-degree warm water.
That is a genuinely staggering, highly physical image to leave on. The sheer heavy reality behind the digital magic we use every day. The X-ray we took today isn't murky or abstract. It reveals a system defined by intense physical pressure, extreme heat, and absolute precision engineering. Thank you for joining us on this extensive deep dive. Keep questioning how the invisible systems around you actually work, and keep exploring the heavy, intensely physical world that makes your weightless digital life possible.